in university-based education, and what I'm going to be trying to do is indicate which messages really translate from formal education to the kinds of initiatives that we're talking about at the conference. One thing I'd like to ask that we often do in our lectures, since digital distraction is really difficult for everybody to deal with, is for the first 10 minutes of my talk, if I could ask for lids down. That is something that we do when we're trying to focus attention on some stuff, and I just want the first part of my talk, the messages, to get through, and then you can feel free to lids up to write down any notes. So thanks. So the University of Colorado at Boulder, we are engaged in a variety of education initiatives. I'll talk about the Science Education Initiative in a little bit more detail, and then talk about a few of the other things that we've been doing. First off, I want to start out talking about why we're engaged in reforming traditional instruction at the university level. Hands up, who already knows about Traxeline?
What?
Traxeline. Nobody knows about Traxeline yet? Excellent. Okay, so it's very important that I tell you about Traxeline. Traxeline is a new form of Zyanter. It's Montilled and Serostana. The Serostanians gristerlate large amounts of Furban and then bracter it to quasyltraxeline. Traxeline may well be one of our most Lucas-Sneslaus in the future because of our Zyanter and Blessed Lich. Okay? So what's Traxeline? As a new form of Zyanter, thank you. Where is it Montilled? Serostana, yes, excellent. You guys are very good students. How is it quasiled? Someone from this half of the room? Good pattern matching, good. And why is it important to know about Traxeline?
It's the most Lucas-Sneslaus.
Yes, it may well be one of our most Lucas-Sneslaus in the future. Excellent. So you're very good students. I'm very happy with you. And what really is Traxeline?
It's something we manipulate to get a good grade.
Excellent answer. That's the best answer I've heard so far. So how does this relate to our university instruction? I mean, this obviously is a sort of metaphor for what can be wrong in traditional instruction. Let me give you an example specifically from physics. So here's a really complicated circuit diagram, bunch of resistors, and if you ask students, find the current through the 2 ohm resistor and the potential difference between points A and B. Pretty complicated little problem, but it's something that you can apply some sort of rules that you would have learned in introductory physics. And students actually do not too bad, like 75% on this question. But now if we ask them a different question in this circuit, explain what happens when the switch is closed, what happens to the current? What happens to the brightness of the bulb? Phenomenologically, what does your answer up here mean in terms of if we hook a couple of bulbs together in a simpler circuit, which one's going to be brighter, which one's going to be dimmer? You might not be surprised, students don't do as well on that one, on this conceptual question. And this is a problem, and this was done at Harvard. This was not a bunch of slouches, these are Harvard students. And it's indicative that there is something missing in our university-based education, in the sort of traditional model of instruction like what I gave you with the Traxeline example, which actually a colleague of mine gives that example to his students at the beginning of every semester, and they dutifully answer the questions that he poses, and then he says, "Shame on you. If I ever say something that sounds like that much gobbledygook, you have to call me on it. You raise your hand and just yell Traxeline, and I'll go back and say it in less gobbledygook messages." So what's missing in that kind of instruction? So my message to you guys, where I'm coming from, is that we need research-driven educational initiatives. We need initiatives that are based not just on what we know works, but on a cycle of assessment and thoughtful goals for our programs so that we can continually improve what we're doing. So to establish testable learning goals and objectives, to use research-based instructional strategies, and then to test to see if it worked. So I'm going to show you some examples of how this plays out. So the Science Education Initiative, let me tell you a little bit about where I'm coming from. So we take postdocs in the sciences and place them within departments. It's a centrally funded project that a department will write a proposal to transform some courses in the department. This is how I was originally hired. The physics department wanted to transform their junior level courses. I came in, I worked directly with faculty to transform the course using this model. So I worked with faculty to talk about what should students learn. So this is the idea of learning goals. I worked with faculty in working groups and I did interviews with them to find out what they really thought those courses were about and what those courses should be targeting. Then we look at what students really are learning. So using research and assessment, so such as interviews, observations, surveys, to find out what's really happening in the classroom. And then see if there's a gap between those two, between what we think students should be learning and what they actually are learning, and then fill that gap with instructional approaches that really make a difference. So we apply teaching techniques that are based on research, and then measure the progress based on those based on those results. So, for example, we might use interactive lectures, using clickers or other instructional methods, reformed homeworks that are really getting students to make sense of what they're learning, group learning situations, and then at the end of the term assess to see whether or not we achieved the learning goals we were looking to achieve. So this is our model. And I believe that it's a broadly applicable model beyond simply university-based instruction, but that's the perspective I'm coming from. So the Science Education Initiative, just so that you get a sense, we consider ourselves a grassroots education transformation rather than top-down, the chancellor or something saying, we need to be teaching in such and such a way. We're taking individuals, working with individuals to change departments from within. And these collaborative conversations that we've had between postdocs like me and the faculty in those departments really have changed the way that faculty think about teaching and learning. So we've had over 100 faculty involved with the program. Over 55 courses are now incorporating research-based teaching techniques. And faculty are also involved in a lot of different aspects of the program, like research and publications. And then we produce publications and resources and assessments and tools and send them out into the world to do good work beyond the university. So that's sort of where I'm coming from. I want to give you an example of a course transformation in introductory physics. So here's an example of testable learning goals. So when I say testable, I do a lot of workshops for faculty on writing learning goals, and a lot of times the first time you sit down to write a learning goal or an objective for what you want students to accomplish, it's a little too vague. It's like, I want students to understand mechanics. I have no idea how to test that. So it's really important to have learning goals that are clearly testable, and it's clear how you would test it. So I always start out with students should. What should students be able to do by the end of the course or by the end of whatever intervention you're talking about? So here's an example from mechanics. Be able to compare and contrast kinetic and potential energy. So it's clear what kinds of things students would be able to do to achieve that. Develop a sense that physics understanding arises from careful experiment, critical reasoning, logic, and sense-making. So a sense of what physics is about. Be able to justify and explain approaches to solving problems. Develop a sense of enjoyment and pleasure about doing this kind of science and reduce their fear of physics. So you can see there are a variety of different kinds of goals we might have, and this is true in university as well as other places. Facts, concepts, these are the sorts of things we typically think of. Procedures, how to do something, how to solve a problem, how to do a certain technique. And attitudes, this is what we often call the hidden curriculum. We often want our students to love our subject, but we don't explicitly do anything to help them love it. We just assume that the loving will come along for the ride if we do a great job of instruction. But as I'll show you, that's not always the case.
Stephanie, let's stay with this slide for a minute. To me, it's very instructive to cross out the first point about specific facts.
Mm-hmm.
All the rest applies to science in general. And it seems to me it's as applicable to what you're trying to do in college, to what you might be trying to do with the middle school course or a high school course.
I'd say that these more sort of general approach and attitude things are you can write a learning goal like this for many different situations, but I also believe that the content has a place in pretty much every science outreach and engagement as well, because that's what is engaging, is the content. It might be different goals for a different type of program, but I think that there are still some content goals that we typically have for, say, a museum exhibit or something like that, because without the content, there's nothing to be engaged with. That would be my take on that. But yes, these are the bottom ones are more general.
I liked your last point about reduce their fear of physics. In a lot of discussions that I've had, and sorry I'm late everybody, but such as travel. I've come to a conclusion, a lot of us have too, that one of the biggest problems we have in physics is that in other subjects, people try to bring you in. In physics, the first thing we do is try to weed you out. You're not Einstein, you're not smart, and that really has a dramatic effect on certain populations. And it's the same thing, like, how do you get across that joy is very, very difficult. And I don't know I'm interested in hearing your tactics. I'm glad you brought that up.
Yeah, let me continue forward, because I get at that a little bit, and if I don't completely touch on it,
Thank you.
make sure that I do. So in the physics education research community, we've created a lot of different assessments to determine how well we're doing at teaching our students. So I want to show you one of them. Who's heard of the force concept inventory? Okay, we've got some savvy folks. So this is a study that was fairly canonical in the physics community and a real wake-up call by Richard Hake. He gave the force concept inventory, which is an assessment on how well students understand basic ideas and mechanics, to students in courses across the country, a bunch of different courses. So what you'll see on the vertical axis when I show you will be the number of courses, the fraction of courses with that particular amount of learning, and then on the horizontal axis is what they learned in that course that they didn't already know coming in. So it's called a normalized learning gain. So here's the results with traditional lecture. We have, some courses that are down here, they're learning around 0.14 of the things that they didn't know, and up here learning around 30% of the things that they didn't know. So the big take-home message is that traditional instruction, students learn less than 25% of the concepts and mechanics that they didn't already know coming in. And that's a problem. There's clearly a gap between our learning goals for those students and what they're actually doing in those courses. So then what about the attitude part? So we've also got this really nice instrument called the Colorado Learning About Science Survey, the CLAS. And it's online, you can use it, you can download it. And it's a survey of how well students gain expert-like beliefs about physics during the course of instruction. For example, there is usually only one correct approach to solving a physics problem. Agree or disagree with that? Obviously, someone who agrees with that has not gained a very expert-like approach to thinking about physics. They've got a whole bunch of different sort of categories of attitudes towards physics, such as Do they see it as something that's personally interesting to them? Do they have a lot of confidence in their ability to do physics, which is what I believe the lady at the back was referring to, whether or not we're really destroying their sense of their ability to do this. So the question should be then, can we, in introductory physics, in just one semester, affect students' attitudes towards science? In just one semester, can we do anything to their attitudes? The good news is yes. The bad news is it's all downhill. All of the purple ones are the big shifts, and you'll notice this big shift in confidence, which is just what you were referring to. And the real sad thing is it's worse for females, that confidence shift.
And it's becoming clearer and clearer why it's taking me years.
And we typically talk about the fact that traditional instruction is not very confidence bolstering, and I can talk about like the gender gap and stuff like that at another time. But traditional instruction is not doing a good job of achieving those attitude goals that we have for our students. One moment. So just the take home being that they come out of introductory classes with more negative attitudes, and if you sort of think about this in terms of like the medical profession, even if they come out learning the content, but we've killed their interest in physics, then I'd say that we've failed. Did you have a question?
Just, the math one is interesting because that's really so if I understand this, that's their attitude about their own feeling about their ability in math. So they came in feeling confident, maybe somewhat, and then they come out of physics realizing, wow, my math is really terrible.
I think that the confidence is actually all in here. I am not one of the developers of the CLS, so I'm not intimately familiar with every question. I believe that the math understanding is more about whether or not how math relates to physics understanding. I could be wrong, and I can take a look at the CLS to understand that more. Yep.
Not everything is negative out there.
That's true. The nature of science is the one that's positive. And since these are all plus or minus 2%, that is within margin of error. I mean, that is without margin of error, so that would be a significant result. So, okay.
So if you look at everything else on that chart, they may be coming out with a negative impression of what the nature of science is. And it doesn't mean that they're sort of have a more positive or productive perspective of what science is all about, if all that other stuff is negative.
Right, like maybe they learned a little bit more what science is about, but they think that it's a real crock and they don't want to engage in it.
So what percentage of these students had high school physics, and why is it what they had at university so different from high school? Maybe in fact they weren't prepared properly for what they were about to face in college.
The preparation problem is definitely something that is talked about when we talk about these kinds of results. I don't want to get too deep into it right now, but I'm happy to talk about it in depth at another time. Did you have?
I did want to contribute with one response, if I may. I don't. There was a recent survey actually taken of high school teachers on the issue of content versus process in educating, and the high school teachers put all their eggs in the basket of content, namely memorization of facts. Almost nothing about process. And when you ask university professors, it's exactly the opposite. I have a strong suspicion that's at play.
That's what I would have guessed.
Thanks, great.
So you're saying that university professors focus on process?
Yes, I know I do when I teach my students.
But isn't that the opposite of here?
But the thing that seems to come across from this is the people teaching college physics, introductory college physics, do not understand the problems of the population that they're dealing with. They don't really know how to reach.
I realize this is all with traditional instruction, so the traditional lecturer with the sea of faces in front of them, so there's not a lot of opportunity for interaction and for finding out where those students are coming from. And I believe that that's a lot of the problem.
Is for the this is introductory physics at CU.
No, this one is introductory traditional physics at CU. The CLAS has been given many times in many different contexts. This is just sort of
Yeah.
our standard set of results
Yeah.
that often comes up.
I mean, just
One more comment and
real
I'd like to
quick
move
comment.
on.
I mean, having been a physics undergraduate myself, I would say that part of my reading of this data is that the professor themselves probably believes at least 1 in 5 of that sea of faces shouldn't become a physicist and would not at all be bothered by this data. So I think there's a cultural, as you said, let's keep them out, which pervades, I think even today, a lot of physics and chemistry teachers.
You don't teach
Definitely.
people physics to become physicists, so that's a small fraction of it.
And the thing that
It's a personal anecdote, it may or may not.
The thing that's
reflect that.
particularly concerning, though, I mean, there are the physics majors who get turned off of being physics majors, but then there's also the other people who, might have gone on to just be regular citizens, but they leave college hating science. And I think that those are the people that this room is probably the most concerned with. Not the people who go on to be scientists, but the people who go on to be regular citizens and end up hating science.
Steve, you talk about the importance of science literacy with people who aren't scientists all the time. It's a big problem that you keep citing. But we go through science education in college only thinking of them as either potential scientists or not. And then we don't think about the impacts of how we treated them when they're in science classes in college. Right?
Yeah, I think that's a very important thing to
They don't just
to
arrive
address.
as adults not liking science or not knowing how to do science.
There's a huge population that needs to be able to make the bridge. That's trained in science but works in other things.
Right, and I would say that university professors oftentimes are destroying the bridge as opposed to creating the bridge.
Yeah.
So,
I'm trying to do that.
So what do we think needs to change? And this is not a new problem. This is something that we've been talking about since the late 1800s in terms of needing a change in science education. But what is new now is that we have a lot more data on what works and what doesn't. So the sort of traditional model of education doesn't really work. Open up their heads, dump in the content, me lecture about Traxylene, you take it away. It doesn't necessarily actually change anything other than them being able to spit back those facts at you. This is called the transmissionist or deficit model of instruction, and it doesn't work. So what we advocate is instead a research-based educational strategy where people actively construct their own understanding. This is something that's in informal education. There are many more opportunities to do this sort of thing, of course, to have this sort of active engagement. In the university setting, we tend to do a lot of group work, clickers and peer instruction, tutorials, case studies, all these things that open up the conversation from just being me lecturing to you to a more back and forth kind of experience where I learn what your difficulties are. So for folks who aren't familiar with those, just to give you a quick sense, clickers and peer instruction, and these are actually used in a lot of museums and such now too. You ask a difficult conceptual question, you have students discuss with their neighbors, that's the critical part. It's not a quiz, it's a learning opportunity. They vote, and you as the instructor and the students get to see where they stand relative to one another, and it opens up the conversation in the class. So those are clickers and peer instruction. Another is changing up recitations. So traditional recitation, TA up at the board with a bunch of students, and he's working problems. We've changed up our recitations to be tutorials where you have students working in groups and a couple of instructors circulating throughout. And so this again offers more interaction opportunity and more of an active learning. So if you remember these results, those results were 25%, most students take away just 25% of what they didn't know. It's better when we add interactive engagement techniques. So, and you'll notice there's this huge spread because there's also a huge spread of the types and implementation of interactive techniques. So you get a much better learning gain, but it's pretty spread out. At CU, when we add clickers, we get modest improvement over just the regular traditional lecture. And we add clickers and tutorials, we get up into the higher echelons of learning. And we see less harm to students' attitudes towards science. There's a very rare class that actually boosts scores on that CLAS exam that assessment that I showed you. It's like those sort of few stellar instructors. Most case, we just do no harm, which, as per the sort of medical ethic, at least we have not killed our patient. So that's our model of educational transformation that I feel is broadly applicable to find it, setting testable learning goals, see what students or participants actually are gaining on those, and then use approaches that have been shown to improve learning to fill that gap. The Science Education Initiative is part of a really broad network of different initiatives at the University of Colorado. We engage in research-based course transformation in a lot of different ways, and I want to just quickly highlight a couple of them. We are creating a center for STEM learning, integrating 50 of the different programs across 4 different colleges, and this is our website. Programs focusing on educational research, educational transformation, and teacher and faculty professional development. So, good go-to place if you're looking for something on educational research. I just want to highlight 2 of those other programs before I wrap up. One is the PhET simulations. Who already knows about the PhET simulations? Okay, some of you. So the PhET simulations, there are over 80, and they're free interactive simulations, all based on education research, tested with students, and run through educational designers to make sure that students are getting the concepts from them that they should be. Here's one of the newest ones, so that even folks who are familiar with them might not know this one. This one obviously is on refraction. You can change the index of refraction of the materials dynamically, and this is a feature of all of the PhET simulations, is being able to change sliders, change a control, and see in real time what happens to the physical system. So they've been shown to be effective tools in a lot of different settings, and they're expanding into middle school. So people who are working with middle school populations, there are a lot of simulations now that are targeted towards that age group, and they've been used in a lot of programs, like after-school programs too. And then the Learning Assistant Program. This is a program that takes undergraduates, trains them in pedagogy, and then they get to apply what they've learned about that pedagogy, working as course assistants and helping students in their discussions in group work and group learning situations in their courses. So it's a vehicle for university transformation and for course transformation. And about 13% of LAs decide to pursue K-12 STEM teaching, which is a huge increase and helps to fill that national need. And if anyone's particularly interested in that program, there is a learning assistant workshop on how to create your own learning assistant program coming up in October.
So it seems like you purposely distinguish that from teaching assistant.
Yes. So teaching assistant is there to help the teacher teach by grading and running recitations and such. The learning assistant is there to help students learn. They're an undergraduate. They just recently took the course, so they're sort of a learning coach rather than someone who's helping the instructor.
And how prevalent is that?
Give me Steve Barry. How prevalent are the learning assistants?
Yeah.
So if we have funding for a certain number each year, and there are always more proposals than we can actually fulfill, but I don't have the numbers right off the top of my head because I'm not directly involved with that program, but I'd say probably around 50 LAs a year, something like that, 30 to 50 a semester involved with courses and helping instruction.
Have you done any kind of analysis to see whether classes that have a learning assistant as opposed to just a teaching assistant score better on the class indicators of confidence and all that stuff?
Oh, I don't know about the class results. They do score better on conceptual assessments. They do learn the material better, but I don't know about the
Give
attitudes.
the impression to the students that there's someone in the university that's on my side here that's trying to help me learn as opposed to the teaching assistant model. It's all the
Right.
teacher.
Yeah, I'm not sure if that research has been done. I'd have to check.
Can I add a comment on this? Laura will know this because I'm from Cambridge and we have one-on-one tutorials or one-on-two tutorials where you have a lot of the techniques that you've sort of described, i.e. demonstrators and tutorials, which are geared towards a Socratic method of learning. And we find that they learn the facts very well, they learn the process very well, they problem solve very well, but their attitudes don't change. And that is a problem that we don't know how to solve. They get very discouraged. I was telling Laura that even after 1 year, so the equivalent of intro physics, we lose 60% of our people into other subjects. So within Cambridge, how we study science is within the broad spectrum of natural sciences, which means you take chemistry as well, etc. And we asked the question, how many of you want to be physicists on day one? And then at the end of that year, we asked that same question, we lose 60%. And the attitude is a problem. They are very good at doing all of the conceptual problems. So I'm sure if we gave them the question that you've been setting them, i.e. questions like, what happens to the brightness of the bulbs, they're actually pretty good at those sorts of questions, as well as the analytical questions. But what doesn't change, even though this one-on-one tutorial happens, is their attitude. And part of my question is, how do I get them to be more engaged?
Well, and I know that there's an upcoming article in the Journal of College Science Teaching on using clickers in peer instruction. I think it was at Harvard, but I'm not certain on that. And they reduced their attrition from the major by adding clickers with peer instruction because there was this more engaged atmosphere was the idea. But you know, your mileage may vary. You know, that's always the case with all this educational
Can I
stuff.
just add that in our report, this is something we looked at a lot because we saw similar numbers. There is one model that looks like it works, and the University of Texas is awesome. They've actually figured out something called a research course, which is very interesting, seems to show a lot of potential for increasing retention numbers. So once again, as I said, our report has lots of resources. In fact, we point to the resources at Boulder for obvious reasons, but UTexas has something very interesting going on.
Is this their initiative to get more undergrads involved in research?
Yes.
Yeah, it's
They do
very
600,
good
yeah,
program.
it's actually an amazing program with the numbers.
Especially with underrepresented
Yeah.
minorities.
Yeah, so as I say, it's a resource that people can look at.
Let me just wrap up so we can get on to break. So my main point is that CU Boulder has a lot of resources for research-based educational transformation. You know, that traditional lecture model doesn't work and students are getting turned off by it. And we have a lot of expertise regarding the university level courses that you know, may and may not be applicable to outreach programs. But that model of determining learning goals, finding research-based educational approaches, and testing whether or not you had an impact is something that I think is really important. I serve as an external evaluator on a lot of programs, and so I know evaluation is often a lot of you know, a piece of a lot of educational programs, but sometimes it's not integrated in such a way to actually allow for improvement of that program. So we were really interested in bringing that experience to the table. And just so you know, I wear a lot of different hats. I am involved in a lot of other educational initiatives, mostly having to do with communicating science and communicating education research through my independent business. And I really focus on disseminating effective teaching practices. I do a lot of video production and audio production and stuff like that. So if people are interested in that sort of thing, I'm happy to talk offline. Any last questions?
I'm sorry, I do have.
Looking at my watch, I set a goal for us to
There is
be,
a question here.
It's okay, I'll do it.
By the way, okay.
so looking at my watch, I set a goal for us to be starting again at 11.